Okay, well, my name is Madison Martin.
I'm Jim.
And do you remember way back when, like the first day of class in reactor physics, he talked a little bit about quantum tunneling and how it has to do with the reason why there's spontaneous and radioactive decay. So we're going to try to give you some background on how that works at a very conceptual level, quantum mechanically speaking. We're not going to do any heavy math in here. We might like give you an example waveform so just so you have an idea that it's a specific shape. We're not going to do any of the hard. It's a lot like what we're doing in neutron transport with the differential equations and stuff like that. You get like harmonics with sines, cosines, and stuff like that. So we're not going to do it.
Have your I believe button handy, because even when you take quantum mechanics, it's more like a geology course. It's faith-based. You just have to believe what we're telling you until the math all works out.
It's just very different than any type of physics you've dealt with before. So to start off, we're going to do show this little joke, and hopefully by the end of this, you should understand why this is funny, if you don't already.
Hey, guys, you will really appreciate this. I read the best science joke on the internet. Alicia, you won't get it, but it's right up their alley. Anyway, so this physicist goes into an ice cream parlor every week and orders an ice cream sundae for himself, and then offers one to the empty stool sitting next to him. This goes on for a while until the owner finally asks him what he's doing. The man says, well, I'm a physicist, and quantum mechanics teaches us that it is possible for the matter above this stool to spontaneously turn into a beautiful woman who might accept my offer and fall in love with me. The owner then says, well, lots of single beautiful women come in here every day. Why don't you buy an ice cream for one of them and they might fall in love with you? And the physicist says, yeah, but what are the odds of that happening?
So that's our little presentation.
Thank you. Now we agree. Okay, we're going to start with a little basic background. Anyone have modern physics even?
And that over there is just kind of an outline of what we're going to cover.
Yeah, we want to do that. Okay, no quantum. You guys did the photoelectric effect at least, right? Mm-hmm. Okay, so keep that in your mind. That's kind of the base underlying principle where a lot of this starts. In fact, after the photoelectric effect kind of spawned the whole, maybe this quantum stuff goes into other places. So that's kind of the start. And you're familiar with this little picture. This is kind of our basic atom with some orbitals, and the nucleons are kind of just thrown in a pile in the middle, all just kind of mushed together. And then the electrons have these nice, discrete energy states where they hang out in pairs. And we're used to the nucleus, just kind of looking like a big bunch of grapes. You know, a lot of these clear. In the nucleus, yeah, they just kind of say, oh, they're all in the middle, don't really worry about it, they're just kind of in a big clump in a pile. But what we know is that there's some kind of order to this thing, because when it makes sense that all of the protons kind of lumped on one side and all the neutrons hung out over here, I mean, do we think that would happen in a nucleus? Just from electrostatics, we know that won't happen. So what this tells us is that inside the nucleus, there's some sort of favorable arrangement of energies where the protons and neutrons have to settle in certain ways. And this led to, there's a couple models, no one really knows exactly how the nucleus arranges beyond the first level. There's a drop model and a shell model, and for this purpose, we're going to look at the shell model just because it makes everything a little easier to understand, and the drop model is all kinds of weird math. So in our shell model, we have energy levels. We won't draw them as circles because the geometry is a little different, and beyond this one, we're not really sure what this is, but these should look a little bit familiar to you. Just like you have K and L, these are the shell levels inside of the nucleus. And S wave scattering, P wave scattering, D wave scattering. Yeah, that's not coincidental exactly. I mean, these things are related, we won't go into that, but and this one is very handy because this is the equivalent of a K shell, And this thing is filled up by an alpha particle. Because in the electron, you can have two shells because of quantum numbers. We have protons and neutrons, and they can both have a spin. So you can have 4 in here, we have 2 in here, and that's your extremely stable helium nucleus. We'll talk about why that's so stable a little later. But that is the essence of that first shell, and the helium nucleus being really stable. So now this leads to our next big picture. Where this is the particle in the box, you know, the kind of the famous first question in quantum mechanics everyone solves, where this is some energy barrier on both sides. And you have a particle trapped in the middle with some energy less than this. Now this particle hangs out, yeah, like photons travel as waves. Well, in this case, the particles are acting like waves. So this is allowed, and what traps the particle in the box is that we set the wave function, which looks like our side. It's a different side, but it's the same idea. That the wave function, you set a boundary condition where the endpoints here have to be at the minimum energy. You know, there's some absolute zero here, but we set the boundary condition so the particle is here. It has to terminate here, and what this turns into then, this is half a wavelength, 1/2 wavelength, and the particle is spread over this wavelength. It's not well localized because we're in a wave mode. So this, if this was an electron in the K shell, it's stuck. And this length in that case is, if you take that K shell and unpeel it to a straight line, that is the length around the circumference. So the electron has to be in the K shell, so it has to fit exactly onto that circle. And so now we have electrons acting like, remember what he said about quantum tunneling through the wall? That's because the matter acts like a wave in these certain cases, and inside the nucleus they do the same thing. We're going to look at this electron. So now this thing can also do this, and it can have multiples of 1/2 lambda, which is, this is the quantum number which is related to the energy, because we're getting a higher and higher frequency as we add in, so it's more and more energy, but the energy will always be less than this, or it'll just escape. But when you get to this boundary, there's this little space here where the wave function would continue if we didn't chop it off with our boundary condition. And this is equivalent, remember, to our diffusion and then our transport. We have this little area in here. This is similar to that, where there's an allowed area, but we're not really allowed. Now, what happens with this one? Why is this allowed if we chopped it here? This is a boundary condition. Do you remember uncertainty? Heisenberg's principle? We've got 2 of these little guys here. We can do it over here. We have this one. So we have some uncertainty in the position and the momentum of this wave. We've stuck it in the box with our boundary conditions, but there's a little bit of wiggle room. Did I put it there? Yeah, it's bigger than that. And we also have the second. Has anyone seen that uncertainty relation before? It's a corollary to where you can't know the energy in a volume or of a particle and the exact time specifically. Just like you can't know the momentum in position, you can't know the energy at an exact instant exactly. You have this minimum factor where you're uncertain. So these things play into this. Now this is a wave, so we know it looks something like some kind of combination of sines and cosines will make the different harmonics. just like in our one dimension, our cosine goes away, so we're left with our sine functions. And there's a probability, because this wave continues on, that this thing, as it's a standing wave, it's bouncing back and forth between the barrier. And there's some chance when it hits here that it will tunnel through. Like this is an almost perfect reflecting mirror with a photon stuck between it, but not quite. And the transmission probability is related to the sine term. We won't go exactly into it, but when you get sine equal to some multiple of n pi, where this becomes 0, the transmission probability is 1. So this is like your reflection probability. So an n and n are the same. So this is related to the quantum number where it goes through. So there's some probability it ekes through, and when you get this exact thing, which we do need this. This potential plus the energy of this particle is what's going to give you the argument in this sine term. This L part of the argument is n pi.
So, Jim, when you say bouncing back and forth, you're talking about it's changing its energy state, or it's changing its physical location?
It's like a standing wave on a string. If you hold a string and I hold a string and we snap half a wavelength into it, the wave's going to just go back and forth between us.
So physically, is the proton or neutron moving, or is it?
The wave is moving, because what happens here, we're going to get to where this thing collapses in a minute, because the electron is somewhere in here. It's not at a given point on this wave. The energy electron is spread over that entire wave. When it interacts with something or we measure it, then this thing will collapse at a set point, which is why when you do probabilities, expectation values, your most probable location and your average location, those are where we expect, those are just functions of where we expect to find it on this wave at some arbitrary time. But so yeah, the electron is actually in all of this spot as a probability function, because psi squared is the probability that we find it. And that's why we set these boundary conditions, so that this area, no matter how many harmonics there are, is 1. So we know it's somewhere in there, absolutely, but where exactly it is, we don't know until we do something.
You know, if you're taking any kind of stats, you're used to normalizing, so that's why you get that area.
Yeah, so the electron is actually in a superposition of all these locations and energies at once. This is the Schrodinger's cat. Have you guys heard of Schrodinger's cat? It's in the box. If we look, we don't know if it's dead or alive, so the cat's dead and alive at the same time. This is like a big box with a bunch of cats, and we don't know which box has the cat in it until we look at it. And if the cat is dead or alive. So you have 2 superpositions, which is okay. So, but because of these uncertainties, when it hits this barrier and bounces back, this value fluctuates just a little bit. And when it's exactly 0, we know it transfers, it can transmit any time. But generally when it hits 1 is when it comes through, because then it has to go through the barrier. And then it's out here, and out here the wave function's unbounded on either side. It does what it wants until it gets trapped into some other energy state. So it will escape. You know, this is the equivalent of the electron just floating around the orbital, doing its thing. It can tunnel out, which is because if you look at the probability, like that probability we're talking about here, if you spread this around the orbital, it looks something like this, except that you get a few of these little dots out here, and you get a few of them even inside the nucleus. There's some probability, the electron's usually here, but there's some probability it's here, and there's some probability it's way out here, without anything else acting on it, just on its own. There's some probability. And so this looks like electron capture, right? There's some probability the electron gets sucked into the nucleus. So that's there. We kind of gloss over electron capture, but that's where this comes from. And that's where the tunneling is that this is the equivalent of all of these dots that are not in the orbital, which is very small and energy dependent. And we need page 2. Okay, we covered that. And this, doing this is actually, this is an I believe button because this thing comes out of, when you see neutron transport, you can see this thing, which is this is another way to write the diffusion equation. If you change what H is, this is now the Schrodinger's equation. And this will turn all the way to this. There's a whole bunch of ugly math we won't go through.
Does anybody take a matrix theory? Or linear? You know what operators are?
Yeah.
Okay, well, think of H as an operator.
Okay.
This thing is a
So
specific
some operator
operator.
defined as something acts on the side.
This thing is a specific operator called the Hamiltonian, and it has one of these guys in it, which you guys should be familiar with. And we saw this solution today. It's a little bit uglier math to get it out here, but it's the same kind of process we went through to get our solution.
And that's why I said like the math for neutron transport is similar to the math for quantum mechanics.
Yeah, this is the solution to a time-independent, one-dimensional Schrodinger's equation. This is one of the solutions which fits into here, but we won't go through all of that. So when this thing tunnels through, we're going to see that, what does this mean physically? This is where the different modes of decay are going to come from quantum mechanically. For your gammas, your betas, your alpha decays, a lot of them fall out of this unless you have some external force acting on them.
Okay.
How about you?
You're going to hand that to me. So this was like a nice overview. We're never going to talk more about specific decay modes. Is it okay if I erase this so that I don't have to write behind me?
Yeah, these are great stuff.
I'll also leave this here. Okay, so let's go back to this picture here, where we talk about the discrete energy states of nucleons and the nucleus. So think of these as discrete energy states. And this comes out of that duality of neutrons having the duality of particle and wave functions. So let's say that they're in some state, but remember we talked about how this alignment is supposed to be in something energetically favorable, something that's more favorable than some other alignment. We wouldn't have the neutrons on one side and the protons on the other. So if the nucleus is in some state that isn't exactly energy favorable, it's going to tend to want to go into something that's more energy favorable. So, and like electrons, where they tend to drop energy levels, same thing here. It's more likely for something like a nucleon to drop its energy level than to go up in energy level. That still kind of stays the same. So let's think that there's some vacancy at a lower level, and this vacancy maybe is caused by some other mode of decay. Now, since it's vacant, something from one of the upper energy states, one of the nucleons is going to want to pop down and fill that vacancy, which will result in a gamma. And then it's kind of, this also occurs in electrons, so it's kind of similar. This will happen from all the energy levels until all of them are stable again, until they're in their normal or fullest form. So that's one way you can think of getting a gamma decay out of a nucleus. Another way has to do with this geometry we were talking about, some energy favorable geometry. It's in some state where it's very close to stable, but not exactly. Say, for example, say this is option 1. So you had some neutron here, like an extra neutron, and you had an extra proton here. Well, really, the nucleus wants these switched. It wants the proton up here, and it wants the neutron down here, so that it's in its energy favorable geometry. But, I mean, what are we talking about? Things don't just like pop up, right? That's kind of a weird thing. Well, we can this has like two options for this to occur. Well, we talked about like this one could quantum tunnel down here and penetrate, then it can fall, I guess. Yeah, so this one could quantum tunnel down here and release a gamma. So you saw the proton. I drove that picture too early.
It'll usually kick it up.
Right, and
It kicks
then,
the proton.
yeah, maybe this gamma is absorbed and that causes the proton to go up a level. So there's that extra energy to push it up to the next energy state. But there's also an option that doesn't include quantum tunneling. And this is another kind of a big phase thing, because we're going to talk about more subatomic particles. So let's say this is a neutron as represented by quarks. You have a down quark, and an up quark. And then this is a proton. Up and down. These are separate. But if they're really close together, they can interact. These quarks can kind of permute here. So like say this could be written as, let's say these two switch. This one can go up and this one can go down. Oh, wait, I wrote that wrong. Alright, that's not it. Okay, let's say this one switches. Okay, it's just one that switches. They don't switch together. When they are two, they switch together. So if one part can switch its direction, it's still. What am I doing wrong?
Your first one's up. You're the first one up.
What happens is strong force, like the electromagnetic force, okay, electromagnetic things exchange protons for their force carrier. Quarks exchange gluons, but instead of positive and negative, there's three of them. It's like a tripole, and we call those colored. But quarks are funny that, like, you know, we have protons are positive, electrons are negative, things are what they are. The quarks aren't quite so rigidly defined. Up and down, when they exchange gluons, can actually flip each other. So that down and up just switch. Part of the gluon, this part gluon plasma, they're less well defined. It's a funny side effect of having a tripole.
Okay, so if like two of them together, they can interact. Like say this one interacts with this one, causing them to switch like direction. So you end up with okay. Oh, I know what happened. I wrote proton neutron on the paper or something. So you really want it down and up from here to interact. Not the other one. So you still have the down from here, but this one's going to switch, so it's going to go up. This one's going to stay up. This one's going to go down. This one's going to stay up. This one's going to go down. Well, look, now we have a neutron and a proton. So they kind of switch. Now, this takes place between here. So now instead of a neutron, a proton, and here you have a neutron. Okay? When this happens, there's also a gamma released. And this thing can really only occur in very limited configuration. So this is limited to certain setups. It's not something that happens universally. So that's another option for gamma decay. Any questions on that? Sorry about that.
It's a little phase-based, yeah. But basically, the strong force acts inside the nucleons, but it also goes outside.
Outside, so like two nucleon strong force can interact with each other, which is how you end up with that split. So what are your other options for decay? I mean, let's think about when you have too many neutrons. So you have too many neutrons in your nucleus. What are your options for decay? How do you get rid of one? Like, how do you solve that problem? You can emit a neutron, right? How common is that? Do you have a lot of neutron emitters? Not really, right? I think of one, California. So, not a whole lot of neutron emitters. So this is obviously not a super favorable option. Well, your other option is a neutron turn into a proton and emit an electron, right? That's another option. And this happens similar to we talked about quarks can switch their directions. Well, instead of it being between two particles, it's just with the one. So you just have the one neutron. Down that top. Well, something happens, and it switches this direction. Now you have a proton, and then some other energy that's released as an electron. And this is possible because the mass of the neutron is greater than the mass of the proton. Like this down quark transition is a little bit more favorable than the opposite, like to go from a proton to a neutron because of this. So this is, in effect, beta decay, beta minus decay. You have a nucleus that has atomic number Z. Now it's going to something else with
A plus 1,
A plus
Z.
1, and then Z plus. And then you know your favorite friend, the anti-neutrino, is not a vector. So that's how this happens on a quantum level. Does anybody have questions about that? So this is how you get beta minus decay. Where the electron comes from? Oh, okay. So the reason why you get an electron out from this is each of these quarks have a charge. So this one is -1/3, -1/3, and +2/3. It has to do with up quark, down quark. So when you come over here, this one stays the same, so you still have the -1/3. This one stays the same, so you have a +2/3. But this one's different. And now you have a +2/3. There's some charge difference between these two particles. What's the difference between -1/3 and -2/3? -1. And out per pops your electron. So that's where the electron comes in all of this. Okay, so now, what's the other thing that can happen in nucleus? You're going to have too many protons instead of too many neutrons. So let's look at that case. Erase this. Now you have too many protons. What are your options to get rid of these? It's kind of similar. You can pop out a proton on its own, right? How many proton emitters are there? Can I do even one? Okay, so your options are you can emit a proton. But as we just talked about, that's not super favorable. It's not common. And in a few minutes, we'll talk about why exactly that's uncommon. And then there's the option where the opposite of what happened with beta, you can have a proton turn into a neutron. And then you have like some other part of it. So this can happen as well. This is the opposite of what we just talked about, which I said is a little less favorable because the mass of a neutron is larger than the mass of a proton. So it would seem like there has to be some additional energy to make this happen. But this is in effect what happens when you have beta plus decay and also electron capture, which he talked about a little bit over there. We're not going to go into too in-depth on these because these are a little bit more complicated to discuss, but that's the basic idea of what happens. So there's some proton that turns to a neutron, and these are two options for that to happen. But we also know that with heavy nuclei, we have this tendency to emit an alpha particle. Right? Everyone knows that lots of things emit alpha particles. This has to do with the fact that, especially with heavy nuclides, you have a lot more neutrons than you do protons, right? So if you pop out 2 neutrons and 2 protons, you're proportionally getting rid of more protons than you are neutrons. Does that make sense? So that ratio of the number of neutrons to protons increases. So you can get rid of 2 neutrons and 2 protons, and this means you're getting a larger portion of protons in your nucleus than you are of neutrons. So this right here is an alpha helium nucleus or an alpha particle. So this tends to occur because, as you talked about, that S1 state, in its full state, is an alpha particle. So it's really energy favorable. So this 2 protons and 2 neutrons is a very strong particle. They tend to get together really well, and they're hard to break up because they're a nice favorable state. So if you think in a large nucleus you have lots of nucleons, right? Well, they can align in little sets of helium nuclei. So you have lots of little helium nuclei together that are together in one nucleus. So it would be easier to break off an entire alpha particle than it would be to break up 1 proton from that alpha particle to kick it out to deal with that problem. So that's why you have a tendency for heavier, especially for heavier nuclides, to emit an alpha particle versus an individual proton. It's more energy favorable for this to occur than it is for that. Any questions on that?
Remember the magic number in the binding energy chart, that giant spike at helium? That's that giant spike that you have to overcome if you try to break apart that helium nucleus. And that energy is much, it's much easier to shift off that whole thing than it is to break a proton out of that.
Right. So that's how you end up with alpha decay. So what have we talked about so far? We talked a little bit about gamma decay. We covered beta minus decay, and we covered alpha decay. We briefly mentioned what's behind beta plus in electron capture, put them in parentheses because we kind of mentioned them. So this is how this all occurs on a quantum level in the nucleus. So if you guys have any questions on this, this would be a good one to ask. Especially, you can ask about any of the other parts too. We can put stuff on the board. Does anybody understand the joke now? You didn't get it before?
Can you explain Schrodinger's cat? The type one more time? That's
Okay.
all I'm understanding.
Yeah, and then if you guys want, we can talk about, we understand the first magic number really, really well, why it happens and what it does. All the other ones, not quite so much. But the helium thing, we can talk about why that magic number exists a little bit if you want, so I know it's kind of said to it. Okay, Schrodinger's cat. This was a thought experiment. And Schrodinger, kind of the godfather of quantum mechanics, because we named everything after him. And he supposed that if I take a cat and I put it in a box and I seal the box up, and I set the box on there and I walk away for some time and come back, and the box is, we don't have any tactile stuff. There's no sound. There's no nothing coming out of the box. It's a black box that's completely sealed. He said, well, we don't know if the cat in the box is dead or alive, but what are our 2 states? We have dead, alive, or dead. These are our 2 outcomes. And he said, well, without any other information, there's an equal probability of each. So, and it has to be, it's discrete, because the cat has to be either dead or alive. It can't be, well, I guess it could be half dead, but we don't allow half dead. So he looked at this as a probability function, kind of like our particle on a string, and he said, well, here the cat's alive, here the cat's dead. And the cat is somewhere on this curve, but we don't know where. So the cat is both half dead and half alive until we look. Which is why if we had, remember our electron that's conveniently trapped in here? The electron is somewhere in here, just like the cat is somewhere in here in its alive or dead state. Now when we look at the cat, we force this wave to collapse back to a point or a particle. So when we measure it, when we interact, when we somehow make this electron do something, or we look at this cat, this wave function goes away for an instant, and it collapses to a single value. Because if we measure the electron at position X, it's at X, it's not at all these different X's. And so when we look at the cat and we go, hey, it's dead or it's alive, now we know it falls to a specific point. But when we don't know, the cat is both dead and alive at the same time, in a sense. As far as our knowledge is, the cat is suspended in a state between dead and alive. And somewhere on this probability distribution is where the cat is. And it's the same thing with the particle. Until we measure it, until it interacts, until we do something to it to look at it. I mean, so in an energy standpoint, you know, an electron has a rest mass and some kinetic energy. That energy is spread out over this wave function. So, like in our orbital, like everyone knows an electron isn't a little ball whizzing around the nucleus, right? It's not a little marble that's whizzing around in a circle. This electron is actually spread over this entire orbital. And with this one has two, you know, and this will go two. So these things are spread over there until something happens to make it interact, until we take an observation. Now, does the observation cause it, or do we happen to observe? That's like Einstein and Fermi and Dirac went back and forth for years over this, and no one really got to a good agreement. But yeah, whether the observation forces the collapse, or whether when you observe it, you happen to see where it collapses with 100% accuracy. Because if you look here, I mean, you'll find it. If we set an electron trap there, we will catch it every time.
So those two electrons in that shell are everywhere at once when you're not looking at it?
Yeah,
It's like a wave function. Remember
it's a
that?
probability function, and there's a most likely value, which this, I mean, it's like this. It's around here. And this is your Bohr radius, which is the most probable value for that electron. And then there's an average value. But yeah, it's not discretely located at any moment in time exactly. Yeah, this is where quantum mechanics is weird, and about 6 months into it, you just realize everything you learned was wrong and accept it and go with it. But yeah, this thing is actually spread out over this, rather than, because, well, if this thing was a ball of negative charge circling around this atom, what would happen?
It'd be emitting gamma.
It's going to lose energy. It's going to fall in, or it's going to emit energy. It's somehow going to have to sustain its orbit. Just like even like when we put the space station up, the shuttle would go up and dock to the space station, and then it'd kick on its thrusters and pick the thing back up, because it's falling as it orbits. And the same thing would happen here. So, but if you suspend this thing as a standing wave around this, we don't have to worry about that so much. It's stuck in a wave state. And it's just a harmonic oscillator, and you know, instead of having two fixed endpoints on a straight line, it's just a circle. So we're okay. I mean, it makes that, it solves the problem of why we don't have this radiation spitting off of everything, or why all the electrons don't crash into the nucleus. Yes, it's kind of weird, but yeah, I mean, from a quantum mechanical standpoint, everything is in a superposition of states. And like you've heard of quantum computers, where basically you take two things and entangle them, and like say I take a photon and I give you a photon, and I entangle those photons. Now the photon can either be up or down. Now when I entangle these, my photon and your photon are both up and down at the same time. We don't know what they are. But if I send you to the other side of the universe and hang you out there, and I open my box and look at my photon and it's up, yours is automatically now down, no matter how far apart you're set. That's quantum entanglement. And that caused a lot of problems too, because in theory you just violated the speed of light, because somehow this photon communicated to this photon what state it has to be in instantaneously across an unlimited difference. And you know, that was another great point of debate between Einstein and Dirac and others. That he said, you can't violate special relativity. He said, I kind of can. And so that didn't go along well. But so why is the magic number of helium so cool? We know this thing really well at the nucleus. Beyond that, we don't really know it very good. But there's a set of quantum numbers. And what? but there are 4 numbers, and you guys have heard of the exclusion principle. What that says is that no particle can have these 4 numbers all be the same, which is why in this orbital, you can only have 2 electrons. N is the energy. This is an angular momentum. This is an orbital angular momentum. This is an intrinsic angular momentum, as if it were like a top spinning. I mean, that's how we picture it. That's not really what's happening. And this is another kind of angular momentum we won't even go into because it's way too, that was like 3 weeks worth of lecture. But so these 4 numbers can't be the same. So when you put an electron here, their ends are the same, so that one's out. Okay, this one has 1 harmonic, so that one's the same, so that one's out. This one is also out, we won't go why. So this thing, its intrinsic angular momentum, which we say can either be up or down.
Those are the same as the Park arrows.
No, these are spin states. Think about it as rotating clockwise or counterclockwise. So this is the only thing that can be different here. So now we can only have 2 electrons, because if we pop a 3rd one in here, these 4 numbers are going to be the same for 2 of them, and that can't happen. When you get out to this orbital, like, you know, we know the first one's a sphere, and the second one's kind of like this thing, and these shapes allow some of these other numbers to change. So that's why you can stick more than 2 in these orbitals. Now we've got this really cool thing that happens with the nucleus, because we have protons and neutrons. So we still can only, in the first harmonic, we can still only vary this number, but now we can have 4 of them, because the proton and the neutron can have the same quantum numbers because they're different particles. So these 4 things lock into this very energetically favorable state, because there's no quantum wiggle room for any of the numbers to be different. Those 4 things stick together, they have to stick together, and nothing else can stick in with them. And so when they get stuck like that, that's like the lowest quantum energy state those things can be in. And so they won't go anywhere without inputting a whole bunch of energy, because you filled every possible quantum state. And that is why that first magic number is well. Now the second ones, they tend to be roughly some kind of multiple of this, but what happens up here starts to get really fuzzy. Just like for Schrodinger's equation, we can only really solve it for hydrogen because it has 1 proton and 1 electron. Everything after that is worse and worse approximations. Unless we take something like iron and take off 25 of the electrons, then we can solve it pretty well. But yeah, so generally if you had 1 positive and 1 negative charge and a nice uniform positive charge, because we think of this as a giant plus, but really around the nucleus there is an electrical field here, because you've got protons and neutrons and up and down quarks, so it's very close to the nucleus. It's not a uniform positive field. So when you have more than 1 proton even, you start to get some weird stuff, which doesn't let you solve Schrodinger's equation really exactly. But this combination of quantum states being absolutely full is why that helium nucleus is so tightly bound and doesn't want to let go. It doesn't even want to let go of one of these, because now it has a vacancy. Just like our stable atoms all the way on the left of the periodic table where their electron shells are full, they don't want to give that up. That's the same thing here. Once they're full, they don't want to give it up.
Any other questions?
Yeah, could you go over the neutron changing to a proton, emitting the electron? I mean, making the electron.
Yeah, it's
With
yeah.
the forms.
Neutrons down now?
Yeah, definitely.
You're talking about with the quarks? Okay. So you have 2 nucleons. Right now, we talked about, when we were talking about the single neutron, how it could go to a proton. Okay, you're
That's
talking,
what you want.
you're talking about beta, not gamma. You're talking about going from here to here.
Yeah, creating.
Okay. Well, this, we'll take out this part, it doesn't matter if either one of us. This could switch its transition, so it can, the down part can switch to the up part. So that's what essentially is happening here. But by doing that, it ends up changing its charge, which is why we ended up with that negative 1/3 is the charge for a down arrow. Negative 1/3. You can think of there as being like little plus signs here if you want this. The net here would be 0. Right?
That's why a neutron has no charge.
And then over here you have 2/3. 2/3. Plus, and then negative 1/3. So one of these stays the same, and one of these stays the same. Or say that's that one. But you have this guy here that has changed its charge. So in order for that change to happen, you have to look at the difference in charge. 1/3 minus 2/3 equals -1. So there's a net change in charge to -1.
And where does that mass come from? What's heavier, the neutron or the proton? So when you go to a proton, you've got this extra energy floating around that can turn into an electron with that -1 charge that came out of the quark transition. And there's still plenty of energy left over.
That's how you end up with that.
Does it change from the down quark to the up quark with quantum tunneling? How does that,
Well, it's a subatomic particle that's switching.
like, how does that change?
Physically speaking,
Yes.
It's sort of quantum tunneling in that it's probabilistic,
yes.
but, I mean, that's a mechanism. I mean, we can't isolate quarks. If we take a bunch of quarks and I throw them out into the air, they will instantaneously congeal into protons and neutrons. Unless you get somewhere around, I think it's like 10 to the 28th or 10 to the 30th on the energy scale, then you can have free quarks. So the properties of individual quarks, other than the whole gluon quark thing, they're kind of nebulous anyway. But if you look at the masses of these, the reason the neutron is heavier is that this is heavier than this. The down quark's heavier than the top quark. Or I mean, the down is heavier than the up. The top's another kind of quark. But so I mean, it's at a higher energy state just in its rest energy, which is why neutrons have a half-life. You know, if I set a bunch of neutrons here, they'll decay. But protons, if they have a half-life, is much, much longer than the existence of the universe, because protons just don't decay that we've ever seen in free space. A proton will stay a proton for all of time, the best we can tell. So yes, this is a more favorable energy configuration than this. And the exact mechanism of what's tunneling where, we just don't have enough data on individual quarks to know that. I mean, we can make a rough wave function based on the mass
So you get back to your wave function, your
and the
probability
binder
function.
and the binding energy, but it's probably in there somewhere. But there's not a really good understanding of free quark behavior anyway, because I think they lasted, I think it was 10 to the minus 200 or 300 seconds after the Big Bang, and then there were no more free quarks. So like in the exact instant the universe popped, there was enough energy for free quarks, and after that, they were all stuck in protons and neutrons.
Any other questions?
Thank you very much.
We did actually calculate you need an accelerator about the size of the asteroid belt if you want to get to that energy to get those free.
Other quark?
Yeah. It needs to be about the radius of the asteroid belt, so we won't be building it anytime soon.